Okay, everybody. So thanks for the invitation and thanks for sticking around for my talk. I hope not everyone's not too sleepy already. I'm going to talk about machine learning in chaotic and turbulent systems, but to be honest, given that we were asked to make the talk accessible to a wide audience, a good chunk of this talk is going to be focused on the machine learning part. I'll begin with fluids and turbulence, which is sort of the thing that gets us out of bed in the morning. It's very awesome and exciting. And then I'll give a pretty shallow and long dive into what the big machine learning picture is. I'll talk about one particular algorithm, neural networks, which are all the rage these days. And then I'll discuss some machine learning meeting turbulence. And actually, there's really no turbulence in here, to be honest with you, but I'll try to give you an overview of what's going on there. And then I'll just talk about some of the ideas that we have for going forward, right? All right, so a lot of people in our institute are working on this. There's Pavlos Marios, is a research associate. Saro, whose picture didn't quite make it up here, but he's not here yet, so don't tell him. Feiyu is one of my master's students. I'll talk a little bit about his work, and Ray is a former master's student that kind of got me started in this whole neural network business some time ago. All right, so I'm going to motivate everything from one of my all-time favorite problems, thermal convection in the geodynamo. I don't work directly on this problem, but I think it's a fantastic problem. Someone once told me, Charlie During, once told me that thermal convection is the most powerful force in the universe. I don't want to be quite that, live that dangerously, so I'm going to say that it drives most fluid flows in the universe. And in a very kind of academic setting, we could look at the Rayleigh-Bénard setup, where you have fluid that's confined between two infinite parallel plates. The bottom plate is hot, the top plate is cold, and everything's inside a gravitational field. And in this setting, if you have a temperature difference that's not too big, heat just conducts from the bottom to the top. But if you make the temperature difference particularly large, then eventually convection sets in, and eventually things become turbulent. I won't say too much more about that, but you should all go see Wally's talk on Wednesday. I think it's at 2:30 p.m., I believe, Wednesday, right? Okay. Now, this simple system here looks kind of academic, but this type of setup exists in a lot of different real physical situations. So here's an example of the Earth cut out. The very center of the Earth is extremely hot, and you could consider that like a very hot surface, right? And then as you go away from the center of the Earth, there's this kind of outer core, which is still very hot. You have a liquid metal that's churning around. And why is the metal in motion? Well, probably because of this large temperature gradient, which set everything into motion. It's also turbulent, and it's a liquid metal, so it happens to conduct electricity. And it's thought that these turbulent fluctuations in the velocity field actually give rise to the large-scale magnetic field, which, of course, allows us to live here on Earth, protected from the solar wind and all sorts of crazy stuff like that. Right? And obviously, there's a lot more physics going on in this setup than in the simple Rayleigh-Bénard setup, but the point is just that the simple idea of this temperature gradient is really quite powerful. Okay, so how might we want to quantify this stuff? Well, maybe we say we're going to look at temperature as a proxy for heat transport, because heat transport seems like it would be important in these kinds of systems. And the temperature, capital T, evolves this little simple advection diffusion equation here. Obviously, things are more intense in real life, but you have your convection term, you have your conduction term. Okay, here's the thermal conductivity. And the U, the boldface U here, is the velocity field, right? And we don't really know what the velocity field is. Well, this is kind of how things are being transported around, right? Heat's being moved from one location to the next. We could solve it, possibly, by our favorite equation, the Navier-Stokes equations, but as we all know in this room, that's analytically intractable due to the nonlinearities and the coupled nature of the problem. Okay, so what kinds of things do these nonlinearities give rise to? Well, they give rise to turbulence, and that's, I guess, why we're all here today. Turbulence is this great problem. What's the definition of turbulence? I mean, people fight about this. I'm sure everyone here has a strong opinion about it. One thing I think we all agree with is that it's a pretty disordered fluid flow, as seen by the great picture by Da Vinci or one of Van Dyck's pictures in his album of fluid motion. Some people say a high-dimensional chaos, but that's kind of difficult to reconcile mathematically or deal with mathematically. I really like thinking about it as a multi-scale phenomenon where you have multiple spatial and temporal scales interacting with each other simultaneously, right? But okay, so nevertheless, turbulence is everywhere. I didn't talk about this picture in the bottom left. This is a simulation of Rayleigh-Bénard convection, 2D, Rayleigh number 10 to the 8th, And these are velocity streamlines colored by temperature. So you have hot at the bottom, cold at the top. And you can see, maybe some people in the front row can see, these small scale circulation regions where the plume is impacting on, or coming up from the surface. Okay. So that's kind of all I wanted to say about fluids, because I think you all know a lot about this stuff already. Fluids are everywhere. We'd love to understand them because they allow us to make scientific predictions, they help us design engineering systems, and really because we're curious and they're beautiful things to try and understand. The mathematical description is challenged. Analytical techniques struggle with this so far, right? In case anyone here is working on doing really cool analytical work, I know there's some cool progress there. Numerical methods, which is where I spend most of my time, also struggle, and this essentially is due to the limited computational resources that we have available to resolve all the scales involved in such motion. A broad approach would be to develop some kind of reduced models. These would be models that represent only the essential physics, and these models should ideally be, let's see if I can get this thing to the point, fast to run, easy to use, and physics reliable. And I'm sure everyone can come up with fast to run and easy to use models right here, but the physics reliable part's really hard, right? What does that even mean to capture the correct physics in these kinds of things? So the question now is, can data-driven approaches provide any new insights into this? Right? And I'll talk a little bit what I mean by data-driven approaches basically in the next part of the introduction. All right, so the big picture. So we're going to put turbulence on the shelf for the moment. Everyone's talking about data science these days. Everyone's creating data science programs for people to study data science. And the reason for this is basically because we now have access to vast amounts of data that we hadn't had before. And when I say we, I mean humans. So I mean even people in the business world and the humanities. I mean, history has a lot of data that we have to sift through, right? So suddenly we're trying to bring new algorithms to bear on understanding these things. For those of us who've been in computational science for a while, we're kind of used to seeing data. But now we have maybe new algorithms to choose from to see how they might help us understand. So machine learning is one family of algorithms, a big family. It aims to use all of this data to train algorithms to learn some tasks, right? The tasks might be learning a mathematical model. Machine learning's had considerable success in a lot of areas, in particular object recognition and image recognition, right? Can you tell the difference between cats and dogs? Right? Machine learning's done really great at that. But on the horizon, I say on the horizon, but actually this is happening now, of course. We want to apply some of these algorithms and reinvent them and change them around somehow to be applied to physical models in fluid mechanics and biology and all sorts of places. And in particular, so people have been doing this for a while, I should say. Let's see how you do this thing. They've been doing physical models. I say it's in the early phases, but people I'm sure were working on this. I know there's some neural networks for turbulence going back to the 90s. But the big question now is, how do you make these algorithms physics aware? How do you embed conservation of mass inside your algorithm so that it's satisfied identically? It's not really enough to penalize that and just say it'll be approximated. We want to be able to predict things in the stars, man. And we know that's probably conservation of mass. Okay, so what are some kind of common tasks that people do in machine learning? This is just to orient you all, in case you're not familiar with this stuff. Classification is a common task. So you're going to assign an input to your algorithm to some category, cat or dog, right? You have a huge data set of images of cats and dogs, and eventually you want your algorithm to be able to recognize a cat or a dog. You could imagine doing the same kind of thing if you had a whole bunch of snapshots of fluids data, and you want to identify if it's laminar or turbulent, right? Our eyes can sort of tell if it's turbulent or not, roughly, right? But could you make an algorithm do that? I'm sure someone's worked on it. I can't think of it right now. Other things that people do is regression models. So you're going to try and predict a numerical value given some input. This would be kind of like learning a mathematical model. In the turbulence world, people have neural networks learn the Reynolds stress tensor, which is some tensor function, right? And they've applied this to the Reynolds average Navier-Stokes equations quite a lot. And we saw a little bit of that earlier today, where one of the presenters was talking about developing a neural network to predict large eddy simulation closures. Oh, and I put this in here. Machine learning can also be used to do transcription and translation. This would be like natural language processing, where you're trying to sift through a whole bunch of like textual documents and extract important features and recommend things. All right. Okay, so let's define some terminology. So we've got your supervised algorithms. This is the idea where you might have some labeled data. So this is a nice looking data set, right? I have no idea what it means. And the yellow stuff is one class, maybe that's cats, and the purple stuff is another class, maybe that's dogs, right? And you happen to have these points labeled for you. So plenty of people on the internet have labeled pictures of cats and dogs, right? So it's already labeled for you. You have access to that data. And now you have a new data point that you take. That's the gray fat one there. And the question is, what is it? And if you've trained your algorithm should be able to identify that thing as, what did I say, a dog? I think I said dog. See, I don't even know. Okay, so that would be a supervised algorithm where you actually take your data set and you actually have the labels already. An unsupervised algorithm, same data set, but has no labels on it. And I think this is a really cool area of research. So one of the famous algorithms in this world is the singular value decomposition, for example. And the goal here is to try and learn maybe clusters or how is your data organized, right? Now here, it's totally unclear to me, from my eyes, where the boundary between these two classes should be. But maybe the algorithm could pick that out. And if I had to guess, I'd guess maybe this algorithm's a little wrong because that purple looks like it should be a yellow. But you get the idea, right? If this algorithm's going to go through without any labels, and it's going to try and pick up some of the structure of the data. One other thing I want to just comment on is sort of a bigger strategy in machine learning. This is the realm of active learning. So let's pretend like this is a classification problem, and maybe you're taking some data from an experiment or astronomy observations or whatever you want to do, and you're trying to learn a decision boundary, right? That's the thing that your algorithm's going to eventually tell you. This is a totally artificial decision boundary, but there it is for you. And the next question is, where should I take data? Where should I take my next data point to update this decision boundary? Right, so from my point of view, I would guess that I probably shouldn't take it here. Right? That point is pretty clear that I might have to spend some money and some time to try and take that data point, and it's going to have no effect whatsoever on updating that decision boundary. I could take the data point down here, same story, and it's not going to affect the decision boundary, but I could maybe decide to take it right there, and then that maybe, if that thing happens to be purple, then it's going to push this decision boundary up, right? So I've spent my time and money wisely to try and figure out how to take the next data point. So this is called the realm of active learning. And these days, there's active learning. Reinforcement learning is sort of a newer version of active learning. That's controversial. Reinforcement learning is not controversial. It's a fantastic field. But whether or not it's supplanted active learning or not, I can't say. So active learning is sort of a big, broad machine learning strategy inside of which many algorithms live. All right, a couple more pieces of terminology here. I think you all have a pretty good sense of what this means. The train-test split, you have a data set, and you're going to run your algorithm on this thing to try and classify it. But it's really unfair to train your algorithm on the whole data set and then to tell everyone that you learned it perfectly, because, it's just wrong, right? It's not quite true. You just memorize the data set. So what people try and do, just because they try to be honest, is they split it into a training set and a test set. The training set usually consists of about 80% of the data. You train it on that thing, and then you say, let me give you the test set, which is still from the same data set, but my algorithm's never seen that data before, never once in its life, and can I predict what classes or what value that should have, right? So that's the idea there. And of course, you could argue that, you're drawing those data points from the same distribution, right? So how generalizable is this really? And everyone's aware of these issues, and it's actually a problem, but at least people are trying to do the right thing. Okay, now I'm going to go a little bit deeper and talk about neural networks. We've seen neural networks already today, but since I'm giving kind of a broad overview of things, I'm going to talk about them a little bit in more depth. So neural networks are universal function approximators, and this was proven rigorously in the late 80s, early 90s, under some fairly general regularity requirements on the function spaces that underlie the neural networks. That basically means that these neural networks doesn't say how to build one, right? But there exists a neural network that can approximate a function arbitrarily close. So it sort of has the feeling of kind of a Fourier series, only a new age Fourier series, if you will. All right, so here's a little neural network. This is called a fully connected network. Maybe you can see why. Every single node is connected to every single other node. So let me talk about the anatomy for a second. A neural network consists of a range a whole bunch of nodes, also known as neurons, also known as units. I'll use them interchangeably. And these neurons are arranged in these layers. And somehow the neurons, whatever's coming out of the neuron, if a neuron fires, it's going to pass its information off to the next neuron somehow. Right? And we don't really know exactly how strongly it's going to connect to the next neuron, but we know it's going to because we said it's a fully connected network. Right? So you usually have like an input layer, and then you have the first hidden layer. You can have any number of width that you want. The width of the network is how many neurons you have in a layer. Then you go to the next layer. That's the second hidden layer. If a neural network has more than one hidden layer, then we call it deep. Just the way the cookie crumbled with that. And then you can have as many layers deep as you want, and then you have an output layer, which is what you're trying to predict. And in this case, I just said the output is just a linear combination of the previous hidden layer. That's a common thing to do in a regression problem. In classification problems, you can choose a whole bunch of different kinds of output layers. All right, so that's the anatomy. Now let me tell you how these things kind of are configured, right? So I have these little equations. So how do you actually combine the information from the previous layer into the next layer? Well, the simplest thing you could imagine doing would be doing a linear combination. So here I've got wx plus b, where w and b are some parameters in the network that we just don't know ahead of time. Problem is, if you do a linear combination, then your output is going to be a linear function, which is not really all that interesting, right? So you have a linear function of a billion parameters. I don't know. Yeah, that's not such a good idea. So what you do is you just hit it with a nonlinear function here called sigma. And I'll talk a little bit more about these later. These sigmas, you could sort of think of them as like a basis. And they're called activation functions, and they basically give you the neural network the nonlinearity. Okay, so what does this thing look like? If you put everything together, you see that the prediction y hat is a composition of these nonlinear functions. W3 sigma of W2 sigma of W1 x plus B plus B2 plus B3. And this nature of the composition of functions was studied way back by Kolmogorov. I forget what decade, 30s or 40s or somewhere around there. Maybe not 40s, I think he was thinking about turbulence then. But he actually studied the composition of functions, right? And people have leveraged some of his theorems to actually prove things about neural networks in the intervening years. Here's some activation functions for you all. There's lots of activation functions. Recently, Google took all the activation functions that people like to use, and they said, what's the best activation function? And none of them were the best, and they made a new activation function. So these things matter quite a lot. One common one is this logistic function. You can see that it has a notion of off, where it's 0, and then it has this quick slope where it turns on and it becomes active, right? And you can change how fast it activates and how steep that slope is by adjusting the weights and the biases in the neural network parameters. Hyperbolic tangent seems to work pretty well, actually. We've used it quite a lot. Same idea, though. It's off at -1 and it turns on at 1. This rectified linear unit down here, this guy seems like an awful idea because it's unbounded, but it turns out it seems to work really well for image classification. You're basically building up a piecewise linear representation of your image, so maybe it's not such a bad idea, and it doesn't seem to have too many issues. It does have some, but we'll ignore those for the moment.
What does the Google thing look like?
Oh, it's the swish activation function. It's x times the logistic, I believe. It's x times the logistic, so it's z times the logistic, and it kind of, what does it do? The funny thing is it's not monotonic, so it actually goes, it's got like a little, stupid thing. I'll show you this later, but it starts here, and then it kind of has a little blip, and then it goes up, and then it saturates. They call it the swish activation function. We've used that one too. It seems to work fine. I don't know why exactly, honestly. Okay, so let's put it all together. Neural network pipeline. How are these things going to work? So you got your input, x, and it goes into the neural network, which you just saw. It's this big black box of complicated connections. And it has a whole bunch of parameters, theta. And then you're going to get a prediction y hat out. And then that prediction, you're going to compare it to data. That's where the whole data-driven business comes in. You have some data, and you're going to compare it in this loss function, or your objective function. And the goal is to minimize that objective function. People like to use the mean squared error. You can choose whatever objective function you want, frankly. And even some new network architectures learn the objective function. These would be things like the generative adversarial networks you might have heard about from time to time. Okay, so you can figure out what you want to choose for L. And then you do like an argmin on this thing to update what the parameters theta are. You get a new prediction, new output, and you continue until your loss function reaches an acceptably low value. Oh, I already said. Okay, so I'll go through this quickly. You do a split. Well, I already told you all the terminology, so I can go quickly. You do a train test split here. Then you do a training validation split. I'll talk about that later. Don't worry too much about that. You're going to optimize the neural network on the training set. You use automatic differentiation in the optimization algorithm. This is basically exploiting the fact that you know the analytical derivatives of the activation functions, so you can compute machine precision accuracy derivatives. Then you monitor your performance on the validation set, and then after you're all done with the training, you go back to your test set and you see what your prediction looks like and you see if it's any good. And here is roughly what a neural net training algorithm would look like. You have some data come in, you're going to get the neural net out, you're going to initialize some parameters, your tolerance on the loss function, and then your step size for your gradient descent algorithm. And then you just loop until the loss function reaches the specified tolerance. You loop over the training data, you get predictions from the neural network, you calculate the loss function, you take a step, update the parameters, gradient descent, and do some validation stuff in case you want to do that, and then you move on to the next step. Right? That's more or less all there is to it. There's stochastic gradient descent, and there's all these other kinds of optimization techniques, and it's not easy, but this is the basic idea of how it goes down. Okay, so quick summary here. So machine learning consists of algorithms to learn complicated functions. There's different strategies for realizing this. I mentioned briefly active learning. There's also reinforcement learning. There's transfer learning, all sorts of different ways of applying these machine learning technologies to your particular case. There's two broad classes of algorithms, the supervised algorithms and the unsupervised algorithms. Neural networks, I kind of focused on them today because they're pretty popular and common. They're universal function approximators, seems like a good thing. There's lots of architectures. I showed you the fully connected network. We heard earlier about convolutional networks. We heard earlier also about echo state networks. You're going to hear a little bit more today about autoencoders by me. There's also recurrent neural networks. I mean, the list just total blowing up. There's tons and tons of architectures. Can neural networks offer anything to scientists and engineers? And the answer is yes. This is an incomplete list of people, so if your name should be on here and it's not, please yell at me afterwards. I made it on the train ride over here yesterday, and I'm sure I forgot some people. I tried to keep it so it's just people who've done neural networks on fluids, but the point is lots and lots of approaches here. Also, if you put an APS abstract in, I didn't cite that here, because for those of you who were in Seattle last week, there were like 4 or 5 parallel sessions on machine learning and fluids, and they're not all published yet, so forgive me. Okay, point is, a lot of people have made progress on this. Okay, so I have a fair bit of, 12 minutes. In the last 10 minutes or so, but the questions are included in that, right? So, okay, in the last 7 minutes or so, I'm going to briefly touch on some of the research that we're doing in our institute around this stuff. Okay, so I'm not going to talk about supervised methods today. A lot of people have worked on supervised methods. My student Ray Feng came up with a whole bunch of neural network architectures that were related to kind of building off some of the physics-based ideas from Julia Ling in her kind of pioneering paper now on learning the Reynolds stress tensor with the neural network. What I'm actually going to talk about today is the self-supervised approach using autoencoders, and I'm going to talk about the unsupervised approach, which is basically using neural networks to solve differential equations. All right, so one of my only equations in this whole talk is this Kuramoto-Sivashinsky equation. So this is a nice equation. You're going to try and find u of x and t, and you got a time term, a kind of Burgers-like nonlinearity term, quadratic nonlinearity. You have a second order term and a fourth order term in space, periodic boundary conditions. And this equation exhibits spatiotemporal chaos, and it's much easier than turbulence. Here's a plot of if I were to do a simulation of this thing and I were just to extract the solution u at a specific location in the domain, just to show you that it's complicated. This is a plot over time of the little probe, and I think it's a mess, right? It's chaotic. Even if you zoom in, you see that there's still a wild fluctuation. It's quite complicated. Now, the Kuramoto-Sivashinsky equation is known to have an inertial manifold, which is a really cool thing to know about it. What that inertial manifold is basically a manifold on which most of the dynamics occurs, and it's a finite dimensional manifold. So that's really really nice, actually. Anytime things are finite, it makes us feel nice about ourselves. And people have studied this, and they figured out for specific parameters of this L. That's L is a bifurcation parameter here. It's the domain length. For different L's, people have figured out what the dimension of this inertial manifold should be. Okay, so enter the autoencoder, which is a type of neural network architecture. The game here is that I'm going to take some, it's called self-supervised because I need data, okay? So I've got some data here, U, and that's my solution, and I'm going to have that solution as a function of x at a single point in time, and I'm going to pass it through a neural network called the encoder. And the encoder is basically a function that's going to map the physical space into some reduced space, what I call Z here. And then I'm going to have another thing called a decoder. The decoder is going to take as input whatever's in the reduced space. It's going to expand it through this decoder, the neural net function, to give me a U hat. And the goal is that the U hat should be equal to the U. And if it is, then I have some idea that maybe whatever's in the reduced space here is somehow a good representation of the underlying, I don't want to say dynamics, but the underlying structure of this field. Okay. You can actually show that if this neural network, if it's a linear, if these are just like linear functions, then this reduced space will span the same subspace as the singular value decomposition. So we're just making it nonlinear, and maybe that buys you something. All right, so what you can do then is you can go into the reduced space here, and you can look at these vector, it's a vector of size n sub d, and I can plot every component. This is for every single snapshot that I get. I can plot every component, and I can see which ones have the most variation. So most of them are 0, but a couple of those components have, not kind of non-zero variation. Okay, so, I have a little bit more here. Okay, so here's a plot, space-time plot of the solution to the Kerr-Moda-Sivashinsky. X-axis is on the x-axis, time is on the y-axis here. I take a snapshot, say at t1000, it looks like this. I throw it through the autoencoder, and I get some kind of reduced representation. Take another snapshot, do the same thing, take another snapshot, do the same thing. I do this for, I don't know, I think I have like 40,000 or so snapshots here, and I'm going to train up the autoencoder, which has something like 100,000, I forget now, 200,000 parameters inside of it. Maybe more. All right, so then I can go and look at the Z's for every single snapshot and see if any kind of pattern emerges. And if I'm just going to kind of go through this movie a little bit, and you see, maybe if you're careful, you can see that maybe it looks like the most variation is kind of starting to align up in a very few number of components here. And eventually, after you do this, 10,000 or 50,000 times, I forget how many, you see that there's basically 8 dimensions. Right. Exactly, yeah. That's a really good point. So what ends up happening here is that these things align up. There's basically 8 dimensions. When I first got this result, I was thrilled because I knew that someone had proved for this dimension of L equal to 22, the inertial manifold has a set dimension of 8. So I got very excited. So then the next thing I did is I tried to, change the dimension of latent space, and it didn't give me 8 anymore. Okay. So there's still some work to be done there, but the simple autoencoder, and it is a very simple autoencoder. It's a fully connected autoencoder. It's able to learn a reduced low-dimensional representation for the Kerr-Moda-Sivashinsky equation. I have a feeling, I didn't tell you, there's a little trick in here. I can talk to you about it later. I have a feeling that this is the inertial manifold. Like this, we learned a mapping to the inertial manifold, but I haven't proven that rigorously yet. So there's some kind of lingering question there. Can we do dynamics on this reduced space? Because once you have the inertial manifold, you might as well do dynamics on it. That'll be much faster than keeping around 1,000 Fourier modes or whatever. I can just use 8 modes of whatever this mapping is. And other people, of course, have begun exploring this area. People came up with really interesting neural networks, a convolutional recurrent autoencoder where they look inside in the latent space and they do dynamics with a recurrent neural network, and they compare the results to proper orthogonal decomposition, and they blow the competition out of the water. It's like really good results, right? So people are looking into this quite a lot. Okay, in the last 56 seconds. Oh, great. Oh, okay, great. Oh, excluding questions. Oh, good. Okay, I can slow down a little bit. So in the last few minutes, I want to talk about solving differential equations with neural networks. So now we're getting even further from turbulence because the equations we're solving with the neural networks are quite simple so far. But I wanted to talk about this because I wanted to talk about some of the unsupervised methods that might be interesting to explore some physics. So and this is one that a lot of people don't necessarily think about a lot. So there's a diagram here, and the thing that's missing from this diagram is data. I don't have any input data coming in here. So I've got some inputs. That's going to be my spatial and temporal domain to my differential equation, x and t, and it goes through a neural net, and the neural net's a function, so it predicts some function, u hat. Now, if that function solves that differential equation that I'm interested in, represented here by Lu minus f equals 0, that could be as complicated as you want it to be. If it's an exact solution, then this will be exactly equal to 0. And in general, of course, it's not. You usually have a PDE residual, which is approximately 0. So why don't we try and minimize that thing? Right? This kind of has inklings of like, the method of weighted residuals, only the weight here. This is kind of like a Galerkin least squares approach in a way, right? Because I'm using the L2 norm squared as my objective function. All right, so then I'm going to try and update the parameters of the neural net here to minimize this residual, and I keep doing this until I get to an acceptably low tolerance. Now, this idea, I don't know. I mean, Lagaris had a nice paper on it in 1998 where he actually showed how you can embed initial and boundary conditions to make sure that those are satisfied exactly. There may have been some work even prior to that that I can't recall at the moment, but this idea is not new at this point. And people like in the Karniadakis group at Brown have been extending this idea in a lot of different directions, including fractional operators and all sorts of stuff. And our group has been looking at how to further embed conservation laws such as energy into this system. I'm just going to briefly talk about it. We came up with what we call, at some point we were calling it a symplectic neural net. It's basically used to solve Hamilton's equations. It's going to conserve energy exactly by construction. And we tested it so far on the Hennen-Hiles system, which is a two-dimensional chaotic system, which we got some what we consider to be encouraging results. What you're seeing here is this phase space portrait of the 2 degrees of freedom. The green line is from a symplectic Euler numerical method, which is not going to track the exact Hamiltonian. It's going to do like a shadow Hamiltonian. And the neural network is, you can't see that because the neural network in a numerical solver, which with very tight error tolerances, fall on top of each other, which we're taking as our ground truth. So the neural network can use far fewer points than the symplectic numerical method, but it's able to, seems at least, able to follow the correct Hamiltonian. And here, this plot on the right is just showing that this is the energy as a function of time. It starts at some initial energy E0, and the neural net just stays constant through the whole time. Symplectic Euler method kind of hovers around the correct energy value, and if you increase the number of points in the symplectic numerical method by a factor of 10, we see that it's a little bit better at conserving energy, but it's still not quite there. Okay, so we're still working on that. We have something on archive at the moment, but we're extending it. Like, we have to go to more Lyapunov times than this. This is more than one Lyapunov time, but it would be cool to do it for like 10, for example. Okay, another thing that we're working on now, this is with Feiyu Chen, who I mentioned at the beginning. He's one of our master students, is developing a software package just to solve neural network differential equations with neural networks. Just to get it out of the air, we could argue about if that's smart or not, right? You're turning in your differential equation solver into a non-convex optimization problem, but that's neither here nor there for now. It's fun to write these software packages. So far, it can do a system, arbitrary systems of nonlinear ODEs. So we'd be really interested to play around with other systems, not just motivated by fluids, but other places too, other physical systems. We have exact satisfaction of initial conditions built into the network. And on the right is your classic predator-prey system. And you can't really see any difference between the neural network and a classical numerical solver. We've also extended it to be able to do 2D canonical PDEs, like Laplace, Poisson, and heat. So this is the Poisson equation solution. On the left here is the neural network solution. On the right, in the middle is the analytical solution. On the right is the residual. It goes down to about 10 to the minus 6. Oh no, 10 to the minus 5 is the largest error here. We can do Dirichlet, Neumann, and mixed boundary conditions. And we're currently, we can also do systems of linear PDEs. So we've done it on laminar pipe flow to see what happens there. It seems to work okay. And Feiyu is currently in the process of implementing arbitrary boundary conditions, pretty arbitrary boundary conditions, and 3D geometries. So that's sort of what's on the horizon. And as with most things regarding neural nets, we are not the only ones doing this, I have to say. Concurrently with some of this, with our current work, there was a group, I think these guys are at Brown, who published a library based on some of the work from Karniadakis that can solve differential equations with neural nets. And this Russian group, I'm not exactly sure where they are, they've also come out with their own package for solving differential equations with neural nets. All right. So let me just do a recap here. So fluids are everywhere. Their behavior is profound. I think we all agree with that. Turbulent flows are multi-scale and hard to model. They're basically what motivated pretty much all this work, just to see what kind of new perspectives we can obtain from some of these different approaches, not necessarily into the nature of turbulence, but just working with turbulent systems. Neural networks might offer new avenues to modeling. So one thing, I didn't talk about it, but I mentioned it, representing closure models from data. That seems to be one of the big successes or really interesting areas. And of course, also solving differential equations. They've been pretty good at that so far. I have, the usual next step slide. We want to consider symmetries beyond just energy conservation. Significantly, can we assess the benefits and shortcomings of neural nets for solving differential equations? Basically, are there any benefits? At one point, we had some preliminary results indicating that they give super exponential convergence over and compared to like fourth order convergence of Runge-Kutta, but that's still very preliminary, so we're trying to hash all that out. Supervised techniques with neural networks for developing turbulence models, and be really cool to explore unsupervised methods for learning turbulence. Things I didn't talk about today, we have some data sets from thermal convection and magnetohydrodynamics, and these, of course, to put more physics into these models is sort of what we're really interested in. Okay, so I can take questions. This is just a teaser slide. There's a neural net, and we want to embed physics in it so we can make predictions about complex systems. It doesn't have to be a neural net. Okay, thank you.
So looking at the Hennen-Hiles problem, for example, we've had good success here when we have approximate analytical solutions to equations solving instead for the residual between the analytical solution and the real solution.
Yeah.
So for Hennen and Hiles, if you Taylor expand it, you get the total lattice with the leading terms and the two leading terms in the Taylor expansion, if I remember. So that has an analytical solution that you can get the orbits that way. And I'd be interested to see if the neural net would do even better at learning the residual.
Yeah.
Because it makes it an easier problem, and it makes it also a very local problem.
I think that's a fantastic idea, actually. We haven't done that, but we're thinking along those lines as well, that neural nets are good at learning the nonlinear parts. And so why don't we do what we can with what we have and then see if the neural net can. I think that's a great point.
May I offer different suggestions?
Sure.
Use the biggest lattice Srini simulated like 24K cube.
Yeah.
Learn your network on that one, and then make it simulate fake lattice 24 million cube.
That would be interesting.
I would love
yeah.
to see the circulation on the 1,000 times
Yeah.
more scale.
Okay. Yeah, that sounds fantastic. Yeah, you wouldn't know if it's right. I mean, so the thing is, so actually this is okay, so he said you wouldn't know if it's right, but this is a key point. So when we think about, I talk about you need some data, right? So let's go back to the turbulence modeling case. For example, you need some DNS data. So you've already run the DNS. Why are you gonna, right? Next time.
Next time you won't have to run the DNS.
Oh yeah, you won't have to run it next time, but you only have one data point, right? So Reynolds number 10 to the 5th or something. And now I want to do a prediction at, Reynolds number 10 to the 7th. Do I have any real generalizability there? So even though I have a huge 24K cube data set, I don't know I don't know how it would generalize, but also to your point, I think that if I tried to run it on a more fine mesh at that same Reynolds number, I think it would do really well. And I think someone in here, is it George? I'm not sure exactly. I feel like it's George. Did something where they're doing like what's called image inpating for turbulence. So the idea here is that you can actually use your neural network to learn to figure out what structures you might have missed in your discretization originally to try and recover the actual field. And they seem to be doing quite well at that as well. So I think it would actually work okay, but I don't know how it would do it a different Reynolds number.
What aspect of turbulence you think will be changing a lot because of machine learning, especially deep learning and things like that? There are many possibilities. I can see the panorama of possibilities. But where do you think it will have the largest impact?
That's a really, really good question. He's asking where I think machine learning will have the largest impact in turbulence. The safe answer is that the place where it seemed to be the biggest impact so far, and that's being the most rapidly developed, which is in the turbulence modeling realm. So, for example, the Reynolds stress tensor modeling, and then the next step is the large eddy simulation, which is going to potentially have some major mathematical hurdles to overcome depending on how you handle the adjoint sensitivities in those kinds of systems. I don't know what that's going to look like yet. But those, I think the engineering community might benefit the quickest from these kinds of models. Now, one thing I would really love to see, I really don't know the answer to this, Srini, but I would love to see what kinds of things unsupervised methods could actually learn. Like, would they uncover things that humans have missed in the past? Probably, but how significant will those be? And I don't know exactly what it's going to look like. Who should we go to? I think Blakesley had, or maybe he's been waiting a while too. But.
Yeah. I want to tell something which is about this question.
Yeah.
Can it detect that there is a lower dimensional attractor behind the turbulence system?
Okay, so I kind of left that on the side. He's asking, can these networks determine if there's a lower dimensional attractor, right? I'm sort of skeptical of that, but this is kind of what I had in mind when I was looking at Kuramoto-Sivashinsky, right? Kuramoto, we know that there's this inertial manifold. Turbulence, we don't know. Probably it doesn't have one, right? So I'm not sure exactly what it's going to find there, right? So I did this same kind of autoencoder on the Rayleigh-Benard system. It's harder because I had a lot of data points. I had to make it convolutional. I had to do all these other things, and the results, I don't trust them right now. So it did learn plumes, which was nice, but I'm a little skeptical as to, I think it's going to be problem dependent, basically. Yeah. Oh, so I'm wondering if we should transfer into the discussion session now, and then we can just keep talking if everyone's okay with that. So I think we're supposed to start the discussion session.
Yeah.
Right, Blake? Yeah.
Probably first we need to thank.
Oh, thank you. Okay, so I think I'm nominally leading this discussion session, so we can just keep talking. I think people are having great questions, so why don't we go to the question in the back? It doesn't have to be directed at me.
Yeah, hi. No, but my question is to you, as it happens. So, if someone mentioned Hino-Hiles versus Toda. Now, in that context, I was wondering if your learning algorithms could spot an integrable system. Right, so because if you really get it right, if somebody gives you data from Toda, is it smart enough to say that the underlying equation is actually this one? And because if it gets it slightly off, it'll be non-integrable.
Yeah.
So I just wonder if that's an amusing game to play on some particular model to see if.
So I don't know. I mean, I know I was talking to someone, so I know I have basically 2 or 3 comments on this, but the basic answer is I don't know. But one thing is, I forget, there's a group who's actually trying to learn Hamiltonians with neural networks, and they're basically trying to detect from data what the Hamiltonian would be. I forget who's doing that work, and that was not related to turbulence or fluids at that point. And then someone else here I was talking to earlier mentioned something along this line, trying to learn equations from the data. And I haven't really seen too much of the neural network world there. There is some work by Steve Brunton, I think, in Washington, on where he has the features of his matrices, not neural nets, but the features are differential operators. So, I mean, people are thinking along these lines, but yeah. Did you have something to comment on that, David?
Yeah. So there's some work being done, actually by some people here. Miles Kramer, who's a Princeton student working with people here, just did some work where he took orbits in a 3-body Kepler system, a Kepler's planetary system with a number of planets. And you integrate the orbits in the system and then use that to train a network to learn the equations.
Uh-huh.
And using that, they've been able to learn that it's a 1 over r squared force as the required force, just given the integrated orbits.
Oh, okay.
And he's been working, I've been working with him at extending that, of training on different data sets of physical systems to learn the laws from that, looking, first starting with some classical problems where we actually know the answer,
Yeah.
and seeing whether it can work on those problems.
Oh, that's cool.
And on the Hamiltonian systems, there's been a bunch of work actually on these Hamiltonian neural nets, where you impose the Hamiltonian as a condition and then train on that. And there's, I know there's some papers coming out of the DeepMind group on that. You know, none of this in the turbulence field, but in neural nets as a whole. And something related to this question of integrability is something that a number of us here have talked some about, is looking at problems in galactic dynamics, where you have large regions of integrability in a galactic potential. So you can describe the tori in the phase space by 3 action angles, and seeing whether we can get the neural nets to learn effectively the action angles by given as the training data, the orbits moving on the tori, and seeing how well it could approximate that, and use that to get kind of analytical approximations to and playing around with whether we can train on fitting a generating function to potentials.
Hod Lipson had done some work on, I think it was a double pendulum. And it wasn't neural nets, but it was learning. Basically, they claimed that they basically learned the Lagrangian mechanics of a double pendulum with like symbolic regression techniques. So you're kind of looking for a functional form with unknown coefficients.
Cool. Blakesley, did you have a comment?
Yeah, I think it was from a few points ago, but I think it's still quite relevant, is there's also the question of how the network is learning. So not just like what it learns and how, and the final product, like, oh, it learned, you know, this Hamiltonian, or it learned these equations, or now it can reproduce this image, cat or dog. But how did it go through all the different steps to get that there? I think that's going to always be a big question mark in everyone's mind, despite how successful these algorithms might be. And so I don't know if you have any comments, or, you know, I've looked into this very superficially for my own dabbling in neural networks, but I would be very curious to know what you think about, you know, in terms of looking at how the networks are actually learning.
I think in general people don't understand how they're working, but I think you know, there's one reason why convolutional networks are so celebrated, because in a way, at least for the image recognition community, you can trace back what they're learning at every layer. Because, you know, they have this notion that in the first layers, they're learning really simple shapes like lines and stuff like that. And then next layer, they're putting a couple things together, so you learn triangles and squares. And then after that, they eventually build up this picture, right? But beyond that, I mean, so on the other extreme of that, actually, there's the echo state networks, which are really magic black boxes. So those things, maybe George might have a deeper insight here than I do, but, you know, you have an input layer and an output layer, and you have this reservoir, and you seed those with random weights, and you fix those. You don't even train on those weights. And the output layer, which is basically like the linear regression layer, is the only thing you're training on. And yet people are able to do very sophisticated dynamical stuff with that. I think people almost don't know really anything about how those are actually work. Do you know how those work, George?
Well, you blow up the dimension. That's the point. If you increase the dimension by a factor of 10 or whatever,
Right. Yeah. So I mean, it's not clear exactly how. I mean, you're making a higher dimension, but I don't know if we can actually trace very clearly through exactly how it's doing what it's doing. And I don't know what.
So if it's basically a black box, I mean, do you think? I mean, we would never basically trust it to go from Reynolds number, 10 to the 3 to Reynolds number 10 to the 7.
So one thing that would be
the challenge for this field.
Yeah, one thing that would be really fun to do is, like, take for example in numerical simulations of incompressible hydrodynamic turbulence, or just incompressible flows in general, you have to make sure that div u equal to 0. Or in MHD, div b really has to be 0, right? And people spend a lot of their careers trying to make sure that this is done properly, right? With really quite sophisticated approaches. One way to do that with a neural network is to somehow put the div u as a constraint, which would just end up being in another loss function. That's the obvious thing to do. But you could imagine, I don't know what it's going to look like, but you could imagine going inside and being like a neural net mechanic and actually carefully turning on and off different connections to figure out which ones are actually starting to violate the divergence constraint. And so I don't know who exactly is going to want to do that, frankly, but I wonder, like, actually truly embedding the physics into the neural network so that you know what it's doing, if that would actually give us a little bit more interpretability. Because you're actually correct that as you go to, if you learn from a data set at some Reynolds number and then you go try and predict what's going on inside of a star, there's no real reason to trust it, right? Your neural net didn't really know about conservation of mass, right? So I think it would be really nice to find a way of actually going inside the guts of the thing, really going inside the guts and forcing it to exactly conserve it. Yeah, what you
like you started out telling about the data-driven approach.
Mm-hmm.
So if we have a purely data-driven approach versus like you feed in loss, you give it a library of functions, like it learns the derivatives, and like the first or second hidden layer learns the derivatives or something like that.
Mm-hmm.
So which works better? Like, is it a purely data-driven approach, or like you feed in some physics into it?
Right. So I think, so if I understood your question correctly, so I interpreted it as like the question of should it be fully unsupervised or fully supervised, and which one works better? Is that roughly what you're thinking?
Well, I mean, you need not have to label the data sets, but you could still say that you could enforce conservation of mass and momentum into, but if you have a purely data-driven approach, you don't know what the hidden layers are learning.
Yep.
So I mean, which one is better? So you interfering somewhere is better or not?
Oh yeah. So actually, there was some work on this by several people, but Julia Ling's the one that comes to mind, where she asked, can a neural network learn the conservation laws? And the answer was yes. And it needs a ton of data, like I forget, either 1 or 2 orders of magnitude more data and a lot more time. And at least in our experiments, when we've actually guaranteed conservation of energy through this symplectic neural network, we converge to within like 2 orders of magnitude faster in the number of epochs that we're training on. So for sure, embedding the known physics into your networks is definitely the way to go. I'm certain about that. Also, we've used sinusoidal activation functions sometimes because sines seem to work pretty well for physics, and those speed things up too.
Okay. Yeah. A quick add question to that. So, if you so on a very superficial basis, does like LSTMs work better? Like if I want to do better averaging compared to a CNN, like if you consider spatial averaging equal to time averaging for a given good number of data sets.
Does an LSTM work for if you want to do an average of? I'm not sure I understand.
Yeah, like if I have a data set for a time series data set and I average over a long period of time, and compare it with to a spatial average.
Okay. Yeah.
So which is better? And like, I mean,
I don't know exactly what situation you have in mind. I can say kind of generally that typically people thought that LSTMs would be good for time series data over convolutional networks, but recently there are these, I forget what they're called, temporal convolutional networks. I forget I haven't read up on them fully exactly how they work. Maybe someone else here knows better than I do, but they seem to be.
That's exactly like you place a CNN on a time series.
Yeah. They seem to be working great. Yeah, I don't know if I don't know. I don't have experience with those guys yet, so maybe they're better. People seem to think they're better. Yeah.
Thanks.
Yeah. So, someone else? Yeah.
I have another question. If you can consider large number of random samples of that chaotic motion which is turbulent, like not just one time frame, but I don't know, 100, 1,000, some number of frames, and you learn your neural network to reproduce you learn that distribution. In other words, your target will not be solving differential equation, but your target will be generating random field with the same statistical property.
Yeah.
And there's a way of doing that. To learn the Markov chain. So if you do that, then you would be able to artificially produce larger lattices from small amounts by tiling them together and using different sampling in each one.
Yeah, I think that's fantastic. Yeah, I agree.
But you're implicitly assuming that they scale.
Yeah.
Well, he should use scale invariant methods. He should not be using methods which are specifically bounded by the sun. You see, like, yes, he should be doing something which will not be just true for that specific box. But even if he does that, by tiling these boxes, you will have a bigger box with different random samples in each one. So boundary may not be so important.
Yeah, I mean, so yeah, it's an interesting idea. I think it's a cool idea. People have done things where they've, going back to the neural net thing, there are these generative adversarial networks which purport to learn the underlying distribution of the data. And people have tried to use those things to learn, turbulence, like statistics up to like 6th or 7th order moments for homogeneous isotropic turbulence with pretty darn good success along those lines, just to add to it, right? I mean, yeah, it's cool. I think there was someone who had to say something up there.
Yeah. My question is about the differential equations part. So
Okay.
if I understand correctly, you're trying to train a neural network so that x and t goes to the field,
Yeah.
u or whatever. But there could be another approach, which is that like most physical models are in terms of time derivative equals something, right? And so that time derivative equals something, you approximate that something with a neural network, and that takes the form of like a recurrent neural network. So my question is like, there is this idea that you generate a lot of data for known equations and then train a neural network to make the computations faster, or look at data for which you don't know the fundamental equations like biological data and try to fit a neural ODE, as they call it these days.
Yeah.
So which one do you think is sort of the way to go forward?
Yeah, I don't know which one's the right. I mean, I think a lot of these questions are. I mean, the neural ODEs approach is really fascinating, and actually, a lot of people are interested in that because I mean, I don't know if people know what those neural ODEs are, where they actually showed that I believe it was with a recurrent neural network, but they proved that in the limit, they're able to that neural network is actually an ODE, right? So they're able to actually use these things as actually differential equation solvers. You can interpret it that way. Another way, on the other side of that, is that if you can actually think of, I talked about the width of the neural network, and if you have like in the limit of infinite width, you can actually show that it can learn an integral, right? So, I mean, I think these are really interesting properties. The kind of the mathematician / physicist in me thinks that that's probably the right way to go because it has a nice connection with like the actual mathematical operators that we're interested in. But the practical person in me says that, if your goal is to actually have these neural networks learn simple models that can be run really quickly for an engineering point of view, maybe that's what you want to do, right? So I don't have any perfect answers, but I think it's going to depend on the application area and what your own interest is in, and I think there's lots of cool, interesting kind of things to do. Does anyone else have? Remember, this is a discussion section. You don't have to only. I mean, I'm glad you're asking me all these cool questions. It's great. Does anyone want to add things? I think you guys all have really good points to bring up here. Does anyone have another vision that they want to share? No? Yeah. I don't know. It's always hard sharing the vision, right? Because there's a darn good chance it's going to be wrong. Any other comments or?
I had a thought listening to the talks today overall, that it seems that the general, especially with these pipe flow and wall-bounded flow problems, that people are kind of moving away from a Navier-Stokes PD kind of approach and looking at new approaches. And I was just wondering if any of the speakers could maybe comment on, like, are we giving up on Navier-Stokes, or what's the feeling? Yeah, Nigel, maybe.
Yeah, I would just say that, I mean, we're not giving up on Navier. I mean, we believe the fluid in the pipe is governed by Navier-Stokes. We're not, it's just that in terms of understanding the phenomena of the universality, what happens in transition, it's maybe not the thing you want to look more broadly. Let's put it that way. You want to look at other ways of understanding what is happening. Yeah.
Yep. Well, that's what I use in my numerical models, so that's
Yeah,
good. And it would be interesting, I think, also for the machine learning side to try to bridge that, right? The Navier-Stokes PD approaches with the simulations, with these kind of reduced models, phenomenological models. I mean, that I don't know if anyone's made that leap yet in terms of turbulence machine learning studies, but that could be an interesting avenue.
Yeah, to my knowledge, took my mic off. Sorry. To my knowledge, they haven't really made that leap, but I think that would be we're just an analogy with the turbulence modeling people, right? I think coming up with this bridge between the fine scales and the coarse scales, the continuum and the subcontinuum scales could be an opportunity for some machine learning models to come. It doesn't have to be a neural net per se. They just happen to be really good at representing complicated functions. But I think there's an opportunity to cross discussion on that.
So Blakely, if I understood you correctly, what you're saying is don't use machine learning to make, say, large eddy simulations or models like that, but use it to try to construct minimal models
Right.
that just satisfy the universal behavior, but not necessarily worry about the microscopic conservation laws and things like that.
Yeah, I mean, I worry with, I I from my point of view, I worry that you can train all day long on Reynolds numbers of 10 to the 3 or 10 to the 4, which is best we can really do with these simulations. But are you ever going to actually trust your network that put out a 10 to the 9 Reynolds number, right? And I don't think anyone will, and that's the problem. So you need to start, I think, simpler and understand what the network is doing. And then once you do that, then you can build on it. And maybe eventually you will get to the point where you feel confident that the network learned really what Reynolds number 10 to the 9 means. But until you step back, I think that's the challenge where this field is at right now.
So I think one thing that's definitely true in the machine learning world right now, I don't think this is controversial, is that it's sort of like playing Legos and building blocks, right? They're these neural nets, and they seem to work on different problems, and people are just trying to put them together in different configurations, and they get better results, but they really don't understand truly how they work. And I've noticed, I mean, it's like low-hanging fruit, right? You can come up with a new network architecture and write 3 or 4 papers on it, and then you move on to the next thing, right? But actually understanding what it's really truly learning and how to make it do that is going to be much harder. Um, and I haven't really seen anyone do anything really. I mean, there's people dabbling, but
So yeah, I mean, with Josh Peak, what we did very basically was to normalize out the amplitude information and just keep the phases in the turbulent maps that we studied, and then we looked at basically gradients of the input image and the output image, and we found that it's very sensitive basically to the phases. And we didn't dive any deeper than that, but it's like, okay, it's learning based on phase structure, not on amplitude structure. It doesn't, when we give it amplitude information, it doesn't really do any better. So it's basically the image, the image side of the neural network is at least definitely learning on the phase information. So that was at least, I think, interesting enough to say, okay, you need to give it some sort of structural information. Amplitude's not enough.
yeah. I mean, So what are you going to do beyond? What's your next step with that?
I don't know. Yeah, I mean, for that study, we were just seeing like, can the neural network basically understand how magnetized the turbulence is in terms of the anisotropy that's present, or any magnetically induced instabilities? Can it visualize that? Whereas sometimes it's very difficult for the human eye. Like, I look at these simulations and I don't necessarily see differences between my different magnetizations in the turbulent flow. And the answer was, yeah, it could do it with like 99% accuracy. And then it's like, well, okay, but why? Why? How is it learning that? And it had to do with the way the magnetic field imprinted phase information on the images. But what we could, of course, keep trying to train on different parameters, but is that interesting, right? And of course, this is a perfect simulation. What we'd actually like to do is to feed it an observation and have the network say, okay, the alpha Mach number is 1 and the sonic Mach number is 10, and we want physics, but definitely the network would break if we tried to give it an observation, or if we added a lot of noise. So we'd have to constantly retrain these things.
Yeah, I agree.
Yeah, it's challenging. It's interesting, but it's challenging.
Are there examples of training on?
Yeah, I think there's quite a few. I mean, this was an MHD experiment that we did, but there's a lot of different groups doing. I think especially interesting is this transition from laminar to turbulent, and training networks on that.
Like, I once in a while on papers that I can't cheese in my brain, right? But like, people are definitely doing this where they or whatever it was, especially in hydrodynamics. I know. Oh, I don't know. What I'm thinking of, I think, was, I don't know. Yeah. We should use your data. 2 minutes or so left. I know everyone wants to go to dinner and whatever. Have any cool observations that they learned from today that they want to kind of close on? Yeah. Yeah, agreed. Yeah. Well, Blakesley, did you have any concluding things since you're the organizer for today?